The deep thrum of the engine reverberates through the deck. 1,000 feet of steel and cargo, a floating city, cuts a path across the vast, indifferent ocean. This vessel, like so many others, is a monument to sheer, uncompromising force. But what happens when that force is not just immense, but seemingly endless? When a machine is built not merely to perform, but to endure, to resist the very forces of time and wear that dismantle everything else? We live in an era of planned obsolescence, where the lifespan of our devices is often measured in years, sometimes even months. Yet, across the spectrum of human ingenuity, there exist true titans, machines engineered with such profound redundancy, such robust materials, and such a surplus of capability, that they defy the conventional wisdom of decay. These are not merely well-built, they are overbuilt. They are designed to last not just decades, but generations, to withstand stresses far beyond their expected limits, and to operate flawlessly long after their designers are gone. Today, we delve into the engineering marvels that refuse to die, the 8 machines so profoundly over-engineered, they could very well last forever. Number 8, the Saturn V F-1 Engine. Imagine standing beside a column of fire hotter than the surface of the sun, generating enough thrust to lift a battleship off the ground. This was the reality of the F-1 engine, the beating heart of the Saturn V rocket. The scale of this machine is almost impossible to comprehend. 5 F-1 engines collectively generated 7.6 million pounds of thrust at launch. Each individual engine produced 1.5 million pounds of thrust, more than the combined power of 800,000 automobile engines. But the F-1's longevity wasn't just about raw power, it was about the engineering philosophy behind it. Engineers designed a single, massive combustion chamber, unlike the clusters of smaller engines often seen today. This eliminated numerous potential failure points and allowed for simpler, more robust fuel lines and turbopumps. The turbopump alone delivered 60,000 gallons of propellants per minute to the combustion chamber, spinning at 5,500 revolutions per minute under extreme temperatures. The true marvel, however, was in the margin of safety. Every component was rigorously tested to failure, then redesigned to exceed those limits. The engine structure, made of nickel alloy and stainless steel, was built to withstand incredible thermal and mechanical stresses. While each F-1 fired only once, for approximately 150 seconds, the design principles ensured absolute reliability. This single-use, maximum tolerance approach meant that if an F-1 were hypothetically cleaned, refurbished, and kept in prime condition, its core structural integrity would remain intact for centuries. It was built as if every single launch was the last chance, a testament to an era where failure was simply not an option. Number 7. Deep-sea submersibles. The ocean floor is one of the most hostile environments on Earth. Pressure increases dramatically with depth, and at the deepest points, it can crush steel as easily as paper. Yet, specialized submersibles routinely descend to these abyssal plains, maintaining habitable environments for their crews. The Mariana Trench, for instance, reaches depths of 36,000 feet, where the pressure exceeds 16,000 pounds per square inch. This is equivalent to placing 50 jumbo jets on a single postage stamp. Submersibles like the Bathyscaphe Trieste, which first reached the Challenger Deep in 1960, and more modern craft like the Limiting Factor, are built with an almost absurd degree of over-engineering. Their pressure hulls are typically spherical, the ideal shape for distributing external forces evenly. The Trieste's crew sphere, for example, was made of 3.5-inch thick high-tensile steel. The Limiting Factor uses a 9 cm thick titanium hull, machined with incredible precision to tolerate imperfections of no more than 0.02 of a millimeter. Every single penetration, every viewport, every electrical connector, is a potential weak point. Engineers employ multiple redundant seals, often with conical shapes that are forced tighter by increasing external pressure, effectively self-sealing. The materials themselves are exotic alloys, resistant to both crushing forces and the corrosive effects of saltwater over extended periods. These machines are not just designed to survive, they are designed to repeatedly venture into an environment that fundamentally seeks to destroy them, doing so with a margin of safety that ensures the lives of their occupants. Their structures are so inherently stable and resistant to environmental fatigue that, short of a catastrophic internal failure, they could maintain their structural integrity for millennia. Number 6. Industrial excavators. Go to any large mining operation, and you'll find colossal excavators, some taller than a 5-story building, with buckets capable of scooping up 100 tons of material in a single bite. Machines like the Bucyrus RH400, or the Komatsu PC8000, are not just big, they are designed for relentless, 24-hour operation under the harshest conditions imaginable. What makes them overbuilt? It starts with the sheer mass of their components. The main boom and stick are often made of high-strength steel plate, several inches thick, reinforced with internal box sections. Their hydraulic systems operate at pressures often exceeding 5,000 pounds per square inch, driven by multiple redundant pumps and oversized cylinders. The slew bearing, which allows the upper structure to rotate, can be over 30 feet in diameter, with hundreds of hardened steel rollers designed to distribute immense loads. But the true longevity comes from their modularity and maintainability. Components are designed to be replaced, not to fail permanently. Engines, transmissions, and hydraulic pumps are often built with significant reserves of power and robust internal parts that are far less stressed during typical operation. These machines are rebuilt and maintained with a meticulousness akin to aircraft. It is not uncommon to find these giant excavators still in active service after 40, 50, or even 60 years, having moved billions of tons of earth, simply because their underlying frames and core mechanisms were so massively over-engineered that they can withstand repeated refurbishment. Their structure is designed for a service life that dramatically outlasts their initial operational components. Number 5. Nuclear power plant reactor pressure vessels. The heart of a nuclear power plant is its reactor pressure vessel, an immense steel cylinder designed to contain the nuclear fuel and the intense heat and radiation generated during fission. These vessels are arguably the most critical and overbuilt components in any power station. Take, for instance, the vessels found in a typical pressurized water reactor, PWR. These can be over 40 feet tall, 20 feet in diameter, and have walls up to 10 inches thick, forged from low-alloy steel. The engineering challenge is immense, containing radioactive materials under extreme temperature, over 600 degrees Fahrenheit, and pressure, 2,500 pounds per square inch, all while being constantly bombarded by neutrons that can embrittle the steel over time. To combat this, engineers incorporate incredibly conservative safety margins. The vessels are designed with no welds in the highest radiation zones to minimize potential weak points. They undergo extensive non-destructive testing, ultrasonic inspections, X-rays, dye penetrance, both during fabrication and periodically throughout their operational life. Crucially, the material choice and manufacturing process itself is designed for longevity. The steel is specially formulated to resist radiation embrittlement, and the entire vessel is annealed, heat-treated, multiple times during production to relieve internal stresses. The design life for many of these vessels is 60 years, with extensions to 80 years now being approved based on extensive metallurgical analysis and monitoring. They are built with such redundancy and robust materials that, barring a catastrophic, external, unforeseen event, their physical containment capabilities are expected to far outlast the generating life of the plant itself. This is an overbuilt system where failure is simply not an option, and the margins are designed to prevent even the most improbable scenarios. Number 4. Certain railway locomotives. For well over a century, the steel horse has been the backbone of industrial transport, and some of these iron beasts simply refuse to retire. While modern locomotives incorporate sophisticated electronics, the fundamental mechanical principles of endurance were established decades ago. Take, for instance, the EMD SW series switchers, first introduced in the 1930s, or the venerable GE 44-tonners. Many of these locomotives, particularly those designed for yard work or industrial shunting, are still in active service today, pushing and pulling freight cars after over 80, and sometimes even 100, years. The secret lies in their rugged, simple design and massive, oversized components. Their frames are often constructed from heavy, cast steel sections, a single monolithic piece built to absorb decades of coupling impacts and track stresses. The prime movers, typically large, slow-speed diesel engines, operate far below their maximum stress points, ensuring minimal wear. These engines are designed to be rebuilt repeatedly, their robust blocks and crankshafts accepting multiple overhauls. Consider the traction motors. In older designs, these were often direct current, DC, motors, built with heavy copper windings and thick insulation, designed to withstand enormous current fluctuations and mechanical vibrations. The gearing in the trucks, or bogies, is similarly over-engineered, massive, hardened steel gears bathed in oil, designed for continuous torque application. This means that while individual components like piston rings or electrical contacts might wear out, the core structural integrity of the locomotive, its frame, engine block, and fundamental mechanical systems, is designed for a virtually indefinite lifespan, provided routine maintenance and rebuilds are performed. They are a testament to the idea that simplicity and mass can be the ultimate forms of longevity. Mid-roll engagement question: which of these machines would you least want to be standing next to? Tell me below. Number 3, the International Space Station. Orbiting 400 kilometers above the Earth, a glittering testament to international cooperation and engineering prowess, is the International Space Station. Launched in 1998, and continuously crewed since 2000, it has far exceeded its initial projected lifespan. Originally conceived for a 15-year mission, the ISS is now approved to operate until at least 2030, with discussions ongoing for even longer. How does a structure in the vacuum of space, constantly bombarded by micrometeoroids and subjected to extreme thermal cycles, last so long? The answer lies in its modularity and redundancy. The ISS is not a single, monolithic structure but a collection of interconnected modules, each designed with its own life support, power, and propulsion systems. If one system fails, others can take over. The station has multiple redundant communication systems, multiple redundant gyroscopes for attitude control, and multiple redundant cooling loops. The station's structure itself, made primarily of aluminum alloys, is designed to withstand the stresses of launch and the vacuum of space. But its longevity comes from its ability to be upgraded and repaired in orbit. Components can be replaced, new modules added, and external elements patched or reinforced by spacewalking astronauts. The solar arrays, for instance, have been replaced and upgraded over time. The false belief here might be that space environments are inherently short-term for complex structures. In reality, with continuous maintenance, upgrades, and a design philosophy built on multiple layers of backup systems, a station in orbit can become a truly generational infrastructure, constantly evolving and renewing itself. The ISS demonstrates that even in the ultimate hostile environment, over-engineering through modularity and repairability can extend life almost indefinitely. Number 2, the Large Hadron Collider's magnets. Beneath the Franco-Swiss border, a 27-kilometer ring houses one of humanity's most ambitious scientific instruments, the Large Hadron Collider, LHC. Its primary function is to accelerate protons to nearly the speed of light and smash them together, revealing the fundamental building blocks of the universe. To achieve this, the LHC relies on over 9,300 superconducting magnets, cooled to temperatures colder than deep space, 1.9 Kelvin, or -271.3 degrees Celsius. These magnets are the core of the machine, bending the proton beams around the ring. The critical component for longevity here is the superconducting wire, made of a niobium-titanium alloy, which conducts electricity with zero resistance at these extreme temperatures, allowing for incredibly powerful magnetic fields without energy loss. Each dipole magnet, used to steer the beams, is 15 meters long and weighs 35 tons. The overbuilt aspect is found in the meticulous precision and redundancy of their construction. The magnets must be aligned to within a fraction of a millimeter over the entire 27-kilometer circumference. Any imperfection could cause the proton beams, each carrying the energy of a moving freight train, to lose focus and impact the pipe, an event called a quench that can damage the magnet. To prevent this, engineers built in redundant cooling systems, sophisticated quench detection systems, and robust structural supports for the coils to withstand the immense electromagnetic forces generated. The design life of these magnets is measured in many decades, with the expectation that they will function precisely for as long as experimental science demands, thanks to materials engineered for extreme cold and an assembly tolerance so tight it beggars belief. They are a monument to enduring precision. Number 1, the world's largest pumps. In the realm of sheer, relentless, and enduring force, few machines match the overbuilt capabilities of the world's largest pumps. These are not your garden variety water movers, these are leviathans designed to shift hundreds of thousands of gallons of fluid per minute, often against immense pressures, in critical applications like flood control, hydroelectric power, and municipal water supply. Consider the pumps at the California aqueduct, capable of moving over 2 million gallons per minute, or the main cooling water pumps in a nuclear power plant, each handling hundreds of thousands of gallons. The secret to their extraordinary longevity lies in their massive scale, conservative operating parameters, and a profound understanding of fluid dynamics and material science. These pumps often employ enormous impellers, the rotating components that propel the fluid, sometimes 15 to 20 feet in diameter, cast from incredibly robust materials like stainless steel or specialized bronze alloys, often many inches thick. The shafts connecting the impellers to the motors are similarly oversized, several feet in diameter in some cases, minimizing deflection and vibration. Bearings are crucial, and in these monster pumps, they are often hydrodynamic bearings, where the shaft actually floats on a film of pressurized oil, preventing metal-on-metal contact and drastically reducing wear. Multiple, redundant seals are employed to prevent leakage, and the entire system is designed to operate well within its maximum flow and pressure ratings, ensuring that components are never unduly stressed. The motors driving these pumps can be tens of thousands of horsepower, themselves built with massive copper windings and heavy-duty insulation for long life. These pumps are designed to run continuously for decades, with maintenance schedules focused on monitoring and preventative care rather than reacting to failures. Their sheer mass, robust material choices, and built-in margins of safety mean that, with proper maintenance, their fundamental pumping mechanisms can operate effectively for over a century, a true testament to overbuilt endurance. Every giant machine hides one piece of engineering nobody notices. Subscribe for the